Okay, so last video we left off here where we were blocking based upon the ABC interaction. Remember with the confounding using incomplete blocks, we would choose a defining contrast that would help us figure out all of the generalized interactions associated with our blocking or our confounding that we included in the experiment. This is really no different except that we're just eliminating those levels based upon a particular contrast of interest. So here, just to finish up, I didn't quite have time to finish up on the last video. Note that the C contrast matches identically the AB contrast, and the highest level interaction ABC is always going to be 1. There's always going to be an odd number of A, B, and C at the high level for this particular design, where I is equal to ABC. So let's compare this to the next. Oops, went the wrong way. Let's try this again, where all of the contrast values for the ABC are -1. So notice I is equal to negative ABC. And this is going to define a fraction where that highest level interaction is -1, always -1. So now the C contrast is the opposite, or the negative, I should say, of the AB. So there's always also going to be an even number of A and B and C at the high level now. So notice how choosing how you block, whether you block for your defining contrast, you either use your block with W equal to 1 or the W equal to -1, is going to be important in terms of the effect on your design. Some of the exercises will help you walk through this a little bit more. So a little note here from Gary: you cannot count on even beginning -1 and odd on even being, that should be being, -1 and odd being +1. Those will change depending on the number of factors in your model, like if you have 4 factors or 3 or 5, and the number of factors for that defining contrast. So everything, just like with the confounding using incomplete blocks, that defining contrast completely determines the effect of the use of the -1 or +1. You really just need to, I wouldn't try to memorize general rules about what's going to happen. I think it's best just to work it out for a particular design and then see what effect you want. So that was everything we were doing there, was dealing with half fractions. If we want to say get a quarter fraction, then we need to define 2 contrasts. So we're going to deal with 2 defining contrasts now, W1 and W2 instead of just W. And then just like with the confounding using incomplete blocks, then we have our sets that are 2 to the 2 levels, meaning the -1, -1, -1, 1, 1, -1, and 1, 1. So let's see an example where our 2 defining contrasts are ACE and -BCD. Don't worry about how these levels for the defining, or these values for the defining contrasts, were determined. This takes some experience and just looking at some examples, but let's see the effect once we know those are our defining contrasts. Okay, so there's a lot to enumerate out here. Let's first take a look at the ACE. Remember that the ACE was our first defining contrast with a +1 coefficient. And so here on the table, it's always 1. Similarly, the BCD was our second defining contrast with coefficient -1. And so as a result, notice if we we see that A, B DE, where does that come from? Notice we have A and B from our two defining contrasts. C, let's ignore for now, but we have a single D and a single E. So A, B, and DE show up one time if we get that generalized interaction between those two defining contrasts. C shows up 2 times, and remember when we operate the coefficient or the exponents of that generalized interaction by modular 2, we get a remainder of 0 for C. And so what's left is A, B, D, E. And so notice all of these coefficients are -1. So this also completely, this completely eliminates the A, B, D, E, because that's our generalized interaction based upon our two defining contrasts, A, C, E, B, C, D. Okay, so that A, B, D, E is always -1. Also take a look at D and BC. It's the negative. They match each other exactly, except they are negative of each other. Similarly, the E and the AC match exactly. Okay, so this is all defined and generated as a result of our defining contrasts. Make sure you know where this table comes from. I'm not going to go through all the details of its generation in the notes, but we can talk about it in class. Okay, so we have an issue here with the fact that the D contrast is the negative, rather not really reverse, but negative of the BC, if you recall this and that. So D can't really be distinguished from BC or negative BC. They are aliases of each other. Okay, this is what we mean by aliasing in these experimental designs. Similarly, E and AC are direct aliases of each other. We cannot distinguish them or tell them apart as we go through those estimating of the particular effects of the model. So Gary here makes a note that in a half fraction, each factorial contrast will come with 2 names or aliases. In a quarter fraction, each factorial contrast will come with 4 aliases or 4 names. Okay, so notice here are our 4 aliases. Negative BC is aliased with D, and then E with AC. What was it before? I don't remember the particulars, but it was, we had A aliased with, I think it was BC before. So we get something by using fractional factorials, but we also have to pay something, okay? The price we pay for fractioning in a 2-series design is that every factorial degree of freedom comes with some aliases, okay? Depending on the degree of your Q, you get more aliases. Notice when the degree of the Q was 1, we had 2 aliases, so 2 to the 1. When the degree was 2, we had 4 aliases, 2 to the 2nd. Within the context of our experiment, we can't find a difference between those aliases, so we lose that information. This is why you want to choose your defining contrast carefully so that you don't alias important effects in your experiment. Gary makes a really important note here that I think we want to pay some attention to for sure. He says if potentially large main effects are always aliased with what's assumed to be the fleas of the experiment, then we're really just getting those main effects. And that's not a bad thing. So perhaps one strategy you can use is to make sure that if you have a very important main effect, such as A, that you know you want to estimate it, make sure that you use a set of defining contrasts so that if it is aliased, it gets aliased with something that is a flea, something that is an interaction that is not consequential to you. That's a good strategy. This just takes, I don't know, I don't use these designs often, but thinking it through and making sure you feel set about your defining contrast just takes time every single time you do it. And it's especially hard when you're not the investigator. If you're, for those of you planning on being consulting statisticians or data scientists, this is a really hard task if you don't understand the context well, and you really need a team of people to make a decision about this. I will note here too, kind of, because I do have a variety of people in this class, that people who are in the sciences, especially engineering and chemistry areas, will probably use a fractional factorial at some point. If you become a classic statistician, you'll occasionally use them. If you work for an engineering college or something, you may use them routinely. If you work as a data scientist, this is one of the major models you need to understand in experimental design, because there are many, whether you're doing like A/B testing for a large corporation, or doing another experiment to test maybe the adequacy of a process within your organization, there are typically a multitude of factors, and you cannot replicate every single treatment combination of those factors. And so this becomes an extremely important, though I'll be the first to admit it's not direct to be able to understand how to implement. I feel like I'm using it for the first time every time I use it. Okay, so a little recap of how our defining contrast affected our aliases. We have I equal for negative BCD, and that implies that D is aliased with BC. So notice that relationship. When I is ACE, E and AC are aliased. If we have I equaled negative ABDE, then we also get AB aliased with DE. This was not actually shown in the notes, but you could work that out on your own and take a look. You could write out that whole big table from a previous slide. I'm going to stop there, and then I'm going to pick up on the next set of notes with finding the alias.